Chapter 7 is about the eigenvalue problem. And I'm going to start by finding some eigenvalues of the Laplacian in a cylinder of radius 1 and height 1. That's a 3D problem, so we have to use the collocation method, and we can use the GUI. So it's a 3D problem. Eigenvalue. One equation. All eigenvalue problems are linear. To solve a 3D problem with PD2D, you have to be able to write the region as x, y, and z functions of three parameters with constant limits. Well, that's easy for a cylinder. Just let P1 be r and P2 be theta. Then x will be P1 r cosine theta, y will be r sine theta, and z is just P3. If you use the interactive driver, you don't even have to enter those equations. You just say it's cylindrical, and it knows the equations for a cylinder. Now the limits on P1, which is r, are 0 to 1, because radius 1. The limits on theta will be 0 to 2 pi. And limits on P3, which is z, will be 0 to 1 again, because height 1. So there's to define the cylinder. We're going to find the eigenvalue closest to 0, which I happen to know is about minus 15.65. We'll modify that number later to find other eigenvalues. We want to call the unknown, we can call it anything we want. Let's call it u. Don't want any integrals. The equation is F1 equals to rho 1 times lambda times u, and so rho 1 is just 1. F1 is the Laplacian of u. Notice we can write it in Cartesian coordinates. Could actually write it in polar coordinates also. You could write u11, that would be the second partial of u with respect to P1, with, in other words, urr and so forth, but we want to write it in Cartesian coordinates. Now the boundary conditions, okay, r equals 0, there's no boundary, therefore no boundary condition, that's the middle axis, it's not on the boundary. R equals 1 is the curved boundary of the cylinder, and that has boundary condition u equals 0. R2 is P2, which is theta, has periodic boundary conditions. P3 at the bottom, P3 is z, so z equals 0, u is 0, z equals 1, the top and bottom boundary conditions u equals 0. Now graphical output, the GUI doesn't give you as many options as the interactive driver does, but this is good here. We want contour plots of P3 equals constant cross sections. P3 is z, so we'll do 5 z equals constant cross sections at 0, 0.25, 0.5, and 0.75 and 1, and we'll plot x and y. And we're done, so let's try running it. CYL3. And we get eigenvalue closest to 0 is minus 15.65 as expected. Let's look at the cross-sectional plots. Well, these aren't very interesting. The cross-sectional plot at z equals 0.25 is circular. It's clearly the solution seems to be symmetric around the axis. This is the z-axis here. The other plots, z equals 0.5, 0.75, look pretty much the same, they're just different scale. So I won't bother showing those. Now, if I want to show, find all the eigenvalues at once without the eigenfunctions, all in the world I have to do is change the parameter I type to 4. It's documented down here. So the I type equals 3 means eigenvalues, but one eigenvalue and the eigenfunction. Change that to 4 and we get all eigenvalues and all eigenfunctions. I mean, all eigenvalues without the eigenfunctions. However, this takes forever to run on this computer, so I ran it on another computer already, and I'll just show you the output. There are the first few eigenvalues, and there's minus 15.65 that we already found. Then there are a couple of them at minus 24.55, a couple at minus 36.27, then there's minus 40, minus 45, minus 50. We notice that the first eigenvalue, the eigenfunction, seems to be axisymmetric. Let's try this one, minus 36. Let's change our EV0R to minus 35 and find the eigenvalue closest to that, which will be this one. And let's look at it and see if it's axisymmetric also. So I want to change this I type back to 3 and only find one eigenvalue. And I want to find the one closest to minus 35 instead of 0. And also, I want to get some MATLAB plots this time. For 3D problems, the MATLAB plots are better than the PD2D plots. So to get the MATLAB plots, all you have to do is remove all occurrences of, see down at the end, you see all these statements that have C explanation mark. So I just have to remove all of those. I can do that with one editor command. And now when I run it, it will not only create the PD2D graphics, but it will generate MATLAB program to generate more graphics. And now this eigenfunction is clearly not axisymmetric. See, there's the z-axis. These are z equals constant. This is a z equals constant cross section, and the solution is not symmetric around the axis. Now let's look at the MATLAB plots. And running that program automatically generated a MATLAB program pd2d.m and a data file pd2d.m will read that data file and produce some MATLAB plots. So let's run it. So that pd2d.m program is all written for you automatically. You don't have to do any MATLAB programming. Just it writes it and writes the data file. And so MATLAB by default does some P3 equals constant cross sections coded by color. Green is 0 because 0 at the top. So here's P3. Those are 5 cross sections of P3, which is Z, and it's clearly not axisymmetric here, this eigenfunction. And here are some R equals constant cross sections. And it's really clearly not axisymmetric. So it looks like some of the eigenvalues of the Laplacian in the cylinder are axisymmetric and some are not. Minus 15.65 was clearly axisymmetric, minus 36.27 is not. If this were a steady state or time-dependent problem and everything is nice and symmetric around the axis, there's no way it could not, the solution could not be axisymmetric. But eigenvalue problems, in spite of the fact that the region and the boundary conditions and everything are perfectly, nothing depends on theta in the original problem, and yet some of the eigenfunctions do depend on theta. So let's solve the axisymmetric problem now. Remember that the Laplacian can be written in terms of R and theta as follows. This is assuming that theta doesn't depend on, phi doesn't depend on theta. We're calling it U. So if you write this out, this will be phi RR plus 1 over R phi R plus phi ZZ. So you can reduce the problem to axisymmetric problem. In other words, write the Laplacian like this. And for those eigenfunctions that don't depend on theta, but some of them do, but for the ones that don't depend on theta, you can ignore the theta derivatives and just set that equal to lambda phi, or we're calling it U, and solve it as a two-dimensional problem, and it's much, much more efficient. So let's solve the two-dimensional problem, the axisymmetric problem, and we should be able to find the axisymmetric eigenvalues, that is, the eigenvalues that have axisymmetric eigenfunctions, and not all of them do. So now we're going to solve the two-dimensional problem, and with R and Z, R going from 0 to 1, Z goes from 0 to 1. And for those eigenfunctions that are independent of theta, we should be able to find those. So now it's a 2D problem. It's a eigenvalue problem, one differential equation again. It's a rectangle. So x, or P1, is goes from 0 to 1, and so does P2, which is, so basically we have to use R, we have to use x for R and y for z. So R goes from 0 to 1, i.e. x goes 0 to 1, z goes from 0 to 1, i.e. y goes from 0 to 1. And well, find the eigenvalue closest to 0 at first. Might as well call the unknown U again. Okay, now the differential equation is u sub rr, which we have to call uxx, plus u sub r divided by r, plus uzz, which, whoops, yy, have to, the variables for a two-dimensional problem have to be x and y. For a three-dimensional problem have to be x, y, and z. So we'll have to call r, x, and z, y. And r11 is 1 again. Now the boundary conditions on R, which is x, again at R equals 0, there's no boundary condition. U is equal to 0 at R equals 1. And Y, which stands for Z, at both 0 and 1 we have U equal to 0. And that's it. Okay, we run that. That ran really fast. And again, we get minus 15.65 as the eigenvalue closest to 0. But, and I won't bother doing MATLAB plots, 2D plots, and PD2D has some plots here. I guess we might as well look at them. This is the eigenfunction corresponding to minus 15.65. And there's the surface plot of the eigenfunction corresponding to minus 15.65. Now let's find all the eigenvalues of the two-dimensional Laplacian, and it's only going to find those whose eigenfunctions are axisymmetric, so it shouldn't show the 24 and the 36. We can see which ones are axisymmetric. So again, we edit the two-dimensional program and change I-type to 4 to find all the eigenvalues. This time it shouldn't take nearly as long as the 3D calculation. The 3D calculation for all eigenvalues is quite expensive. 2D not nearly as bad. So just change that to 4 and run it. Now it won't find any eigenfunctions, but it'll find all the eigenvalues. And there are the eigenvalues, the first 50. So minus 15.65, and the next one is minus 40, and the minus 45. Notice it skipped the minus 24 and minus 36. Those two eigenvalues had eigenfunctions that were not axisymmetric apparently, whereas minus 40, minus 45 are axisymmetric eigenvalues. That is, their eigenfunctions are axisymmetric. So basically these are a subset of the 3D ones, and some are axisymmetric and some are not. As I said, it seems a little strange because steady state or time-dependent problem with where the region and the boundary conditions are independent of theta. You'd expect the solution would have to be independent of theta, but for eigenfunction problem, that's not necessarily the case. Some of them are and some of them are not. And the book starts out with the application, which is the Schrodinger equation, where phi is the probability density, or the square of phi is the probability density, but this is an eigenvalue problem. It's fundamental to modern physics, atomic physics. E is the energy of a particle, and phi is the probability distribution, or phi squared is the probability distribution. V is the potential energy field, and you're probably familiar with the case of the hydrogen atom where you have an inverse square potential field. So that V is proportional to 1 over the distance to the origin where the proton is. Phi represents the probability distribution of the electron, and E is its energy. And you find the eigenvalues of this. You can actually find them analytically. They're well known. And some of them are spherically symmetric and some are not. The first one, for example, minus 13.6 equals minus 13.6 electron volts. Here's one cross section of the probability, the eigenfunction, and it looks like it's spherically symmetric. You know, the potential energy is a function of rho only, so you'd expect that the eigenfunction would be a spherically symmetric also. In other words, not axisymmetric now. We're talking about depending on rho only, where rho is the square root of x squared plus y squared plus z squared. And the first eigenvalue is spherically symmetric, that is, its eigenfunction is spherically symmetric. The second one, well, as I said, the first one is minus 13.6 electron volts, and then there's 4 at minus 3.4. And one of those is spherically symmetric, the other 3 are not. And then there's 9 at minus 1.511. And one of those is spherically symmetric. So you can find the spherically symmetric ones by reducing this to a one-dimensional problem. And that's what we do in one of the homework problems. So if your eigenfunction depends only on rho, as some of the eigenfunctions do and some don't, then the Laplacian can be written as phi sub rho rho plus 2 over rho phi sub rho. And so you can solve it as a one-dimensional problem, but you'll only find the eigenvalues that are spherically symmetric. Another homework problem is the Schrödinger equation where you have 2 protons, one electron and 2 protons, H2 molecule, and so the potential energy is 1 over the distance to the first proton plus 1 over the distance to the second one. And solve this as a 3-dimensional problem, and you get several eigenvalues. And PD2D has a unique way of plotting functions of 3 variables, which involves drawing contour surfaces. And the next page they're shown, let's see. Here's the eigenfunction corresponding to the first eigenvalue of that 2-proton system. And down here is the eigenfunction corresponding to the third eigenvalue. And let me show you these in color, because in the book they're not in color. They look a lot better in color. So let's look at these 2 plots in their original form. Well, here's the PD2D. This is not a MATLAB plot. This is a PD2D plot. It draws the some contour surfaces of the eigenfunction, and they're coded by color. You can see where the 2 protons are. They're the blue, its highest probability close to the proton, to the 2 protons. This is the first eigenfunction. And here's a little better look at the eigenfunction corresponding to the third eigenvalue. The levels are coded by color again. It looks a little better in color. And in fact, here's the MATLAB plot for the hydrogen atom. The first eigenfunction that one cross section at the equator, you can see that it looks like it is spherically symmetric, although you can't tell for sure, but it looks like it is. I just showed you this, but this is in color, so this also looks better in color. And here was the other plot that in the book it wasn't in color, so here it is in original color, and it's clearly not spherically symmetric. This is the eigenfunction corresponding to one of the second eigenvalues, which is not spherically symmetric. It's one cross section at longitude equals constant.